Okay, we're going to now look at the famous matching problem that utilizes the inclusion and exclusion property, which makes a problem that can seem kind of hard to solve quite nice and easy. All right, so here's the setup. We have N men going to a party wearing hats, and once they get there, everyone throws their hat into the center of the room. Okay? The host of the party mixes up the hats and randomly hands them back out to each of the men. Okay, so now all the men have some hat that they were handed to by the host. What is the probability that none of them got their own hat? Okay, so our goal is in this problem is to reframe this so that we can utilize that identity. All right? So sometimes, as we have talked about before, it is easier to solve, let's see how I can change that color. It is easier to solve a question by finding its complement, right? So the probability, let's write this down. The probability that none get their own hat is equal to 1 minus the probability of the complement of none, right? So whatever the complement of none is, the probability of it, we subtract from 1, and that'll give us the probability of none. Okay, so the next question is, what's the complement to none? Right, so what is none complement? Well, it's not all, right? So it is at least one man gets his own hat. Okay? So to find the probability of none, we're going to find 1 minus the probability that at least one man gets his hat. Okay? All right, so maybe finding this won't be so bad. So what should at least one be? Well, let's see if we can, that just means that one of the men have them, right? So let's now name our events based on that scenario. So let's let E sub 1 be the event that the first man, or man 1, we'll say, gets his hat, his own hat. Okay? And then E2, that's the event that man 2 gets his own hat. And so on. All the way down to, we should say, E sub big N, because I have N men, is the event that man N gets his own hat. All right? All right, and since we want at least one of them, that just means one or more than one, right? So really, the probability of at least one man is equal to the probability of E1 union E2 union and so on, all of them, right? Just means to be in the union, you just have to be somewhere in one of those sets. Could be in all of them, could be in some of them, could be in exactly one of them, but you will be in at least one of them. Okay? So now we have reframed this question to the probability of the union of sets. Here's where we're going to utilize the inclusion-exclusion principle, okay? So let's write out what it would be, the principle again that we got from the last, right? So E1 union, E2 union, all the way up to E sub n is equal to the sum of the probabilities of each E sub I, right? I equals 1 up to big N, minus the sum of all the pairings, right? So we did E sub I1, E sub I2, because we don't know how big N is. And we put the restriction that I1 is less than I sub 2, right? And then we add the triples and so forth, all the way till we get to this last step, which we know we want them to be negative when it's odd and I'm sorry, negative when it's even and positive when it's odd. So we're going to take the subtract or add off the intersection of all of them. That's kind of weird. E sub n. Okay? So that's just it reframed, just using our identity. We still have to solve it. Okay, but maybe it's not so bad as we think. So let's just go explore the probability that E sub 1, that the first guy gets his hat. Okay? So let's now look at this as a counting problem. So we've numbered our men somehow based on maybe when they arrived, such as that. Okay? So what we're really saying is man 1 gets his hat, and then we don't care what happens to the rest. So remember, we're going to deal with the overcount by subtracting and adding and subtracting and adding. So we don't care about what happens to the rest. All we care about is, does man 1 get his hat? There's one way he can do that, right? He gets it. And then where the other hats go could be anywhere in this list from 2 to n, right? So it's really like the permutation of, oops, let's come down here. It's the permutation of the remaining n minus 1 hats, because he got his hat, divided by all the ways you could permute the hats, right? That's P sub E1, which really reduces to 1 over big N, right? And in fact, you could make the same argument for P of E2, right? It's really just saying, I don't care what happens anywhere else, but this guy gets his hat, which really means I'm going to take the remaining n minus 1 and permute them over all the ways you could permute the hats. And in fact, you go, oh, I see, it doesn't even matter which E sub I it is. So the reality is the probability of E sub I is equal to n minus 1 factorial over n factorial, which reduces to 1 over n. Okay, so when we go put this back into our formula up here, we know that this is 1 over n for every n, and we have n of them. Okay, so that first summation becomes 1. All right? All right, let's see if finding the other two is easy. So let's start again with maybe that E sub 1, 2, right? First man, second man get their hat. So what does that mean? Well, it's the same idea, right? So they get, 1 gets his hat, 2 gets his hat, and really I have the remaining n minus 2 hats to permute over all the ways you could permute the hats. Okay, so this actually becomes, what? 1 over n times n minus 1. Right? Actually, let's not reduce it quite yet, because you'll see in a minute. The question is, all right, so we're going to replace, so, oh yeah, again, we see this is true for E1, 2, and I bet you could convince yourself this is actually true for any of the pairs, E sub I1, E sub I2, oops, I2, where I1 is less than I sub 2, right? That's going to be true no matter what. We don't care what happens in the other steps. Don't worry about the overcount, right? So that means this piece right here becomes, what do we say, n minus 2 factorial over big N factorial. Now the question is if I'm going to add them all up, how many of these do I have? And they're exactly the same. Well, I have n pairs, and I'm going to choose 2, right? I'm sorry, I have n men, and I'm going to choose pairs, so groups of size 2. Okay, I'm going to erase this stuff right here because it is currently in my way. All right, back to the pen. So what does this become? This becomes n factorial over n minus 2 factorial, 2 factorial times n minus 2 factorial over n factorial. And look what beautiful things happen. Dun, dun, dun. And I'm actually left with 1 over 2 factorial. Ooh, what do you think the third one's going to be? I bet you'll be able to figure it out pretty quickly. Okay, so let's now consider what happens when we take e sub, I'm going to say I1, e sub I2, e sub I3. Okay, that just means three of them where they're ordered, right? So I1 less than I2 less than I3. They get their hats, which means those are fixed. And really, we're going to take the remaining n minus 3 hats, permute them over all the possible ways to permute the hats. Guess what? We're going to come over here, which you don't see it, so it's really the one that's embedded there. It's going to be, so that was a minus, right? There's a minus. Then we're at a plus. What I say? N minus 3 factorial over n factorial. And the question is how many groups of size 3 do I have out of the n men? Well, that's going to be n choose 3, right? And guess what's going to happen? That's going to become n factorial, n minus 3 factorial, 3 factorial times n minus 3 factorial, n factorial. Same thing as before. And I'm going to be left with 1 over 3 factorial, but this time it's a plus, right? So what I have going on here is 1 minus 1 over 2 factorial plus 1 over 3 factorial, and I bet you can convince yourself that the next one is going to be minus 1 over 4 factorial plus 1 over 5 factorial minus and so on until you get to, well, this one is a tricky one, so we're going to do plus minus 1 to the big N plus 1. And the question is how many ways can all of them get their hat over all the ways that you can distribute the hat. So that's really 1 over n factorial. Okay, now that's kind of cool. So let's reframe our original question, which was this union. Okay, so the probability, at least one person gets their hat, so the probability of E1 union E2 union ... union E sub n is equal to 1 minus 1 over 2 factorial plus 1 over 3 factorial, and so on all the way up to plus minus 1 to the n plus 1, 1 over n factorial. Okay? That's the union. But that's not actually what I wanted. I wanted none, remember? So none is going to be, so the probability of none, which is the question I wanted, is 1 minus that. So it's 1 minus 1 minus 1 over 2 factorial plus 1 over 3 factorial, right? Minus and so on, plus minus 1 to the n plus 1, 1 over n factorial. Right? And I know you're going to be very tempted to subtract those ones, but I don't want you to do that, okay? I want you to leave it like this, but I'm going to rewrite this now as 1 minus 1 plus 1 over 2 factorial minus 1 over 3 factorial, plus and so on, and this time this becomes minus 1 to the n, right? Because I distributed that negative to this. So you could say n plus 2 or just n, okay? Now, so this actually is the answer to our question. This is the probability that none of them get their own hat. But let's ask what this gets closer to. So what if your big N gets really large? Okay? So like a gajillion men go into a room and throw their hats. Well, then we kind of curious where this thing is headed. So I want you to remember something from Calc 2. So recall that if you take the sum, this comes up a lot in our class, of n equals 0 up to infinity of x to the n over n factorial, you get e to the x, which, by the way, is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Remember that? Now, if x is equal to -1, then e to the negative x should be equal to 1 minus 1 plus 1 over 2 factorial minus 1 over 3 factorial, and so on. Yes? Which is, by the way, what this thing is headed towards as n gets to infinity. So, as n, if n is going towards infinity, the probability that none of the men get their hats is approximately e to the -1. Sorry, I don't know why I have negative x there. Let's fix that. What I mean to say is if x is equal to -1, then we have e to the -1 equals this. So again, the hats are just a way to describe this, but really you're talking about indistinct things. Like there's an associated, we could say with anything, like n people have a Social Security number, and then I mix them all up and then I redistribute those numbers. What's the probability that no one gets their number back? Well, it's approximately e to the -1 if n gets really, really big. It's kind of cool stuff. And so we're going to look at examples where we have problems that we want to reframe as a union or 1 minus the union or probability of the union to answer that question. It's very cool stuff.